report. And let me just also quickly introduce our distinguished panelists today. So today the topic is game-theoretic probability in physics, and we're very pleased to have our very own Glenn Shafer, who will be going first, setting the stage, and then we will have Dustin. Sorry, I don't know how to pronounce your last name. Lazarovici.
Yeah, Lazarovici technically.
Lazarovici from philosophy, Lausanne, and then Leah Henderson from philosophy, Groningen, and lastly, Eddy Keming Chen from philosophy, UC San Diego. So it will be a very fun discussion. Just to remind everyone that the presentation for each speaker will be 10 minutes. We're going to try to keep time strict so that we will have enough time for discussion. And I will give you a heads up if you're running out of time. So Glenn, please feel free to take it away.
Okay, well, as you know, I am an expert, perhaps one, we have Lloyd is actually listening in on this. And Phil David is a pioneer in these ideas too, but I can count myself as an expert in game theory probability, certainly not in physics. So I'm going to make some general comments about game theory probability. It's an alternative, we think of it as an alternative, at least in discrete time, to measure-theoretic probability. And what is its value? As I see it, its main value, an important value of it is that you can prove the same things with less assumptions. So to begin with, you don't need to assume, I'm talking about discrete time, you don't need to assume measurability conditions, and you don't need to assume what Kolmogorov called continuity, which in his context is equivalent to countable additivity. So you don't need to assume either of those, measurability or countable additivity. Now that's not a dig at Kolmogorov, because he was very clear that those ideas, countable additivity and measurability, are not something inherent to the idea of probability. They're just mathematical idealizations or convenient assumptions in order to use measure theory as a tool in probability. So the fact that we can do it without that is something I think that Kolmogorov would not find scandalous. I don't know how interested he would be, but I don't think he'd be scandalized by it. The second thing we don't need is that we don't need to have complete probability distributions. We don't need to have a probability distribution for this. We can do decision theory without probabilities for without having probability a probability measure that tells us probabilities for what the decision maker will do. And we can also don't need probabilities for what a forecaster is going to do if the forecaster is giving probabilities step by step. So these are ideas that, as I say, Philip David pioneered, excuse me, who's in our group. So I'd be interested in his thoughts. So this brings us, this fact that we don't need probabilities for the decision maker or for the forecaster brings probability actually closer to what people are doing in machine learning and engineering, because in engineering we've had control variables for which we don't give probabilities. We decide what values to set them to. In statistics too, because we have, in most applications in physics, we have independent variables, so-called explanatory variables like the x's in a multiple regression that we don't give probabilities to in many applications. In fact, I would say most. So it's very much, maybe in some places, closer to what how people actually do applied probability theory, or at least applications in fields such as statistics, engineering, and machine learning. So this raises some philosophical questions. We've become accustomed, mathematicians have been telling us that measure theory is the right framework, that we need it for a rigorous theory. And if you accepted that, then understanding a probability measure is how you would try to understand probability philosophically. So I have a quote from Alan Hayek. I looked up his article on interpretations of probability in the Stanford Encyclopedia of Philosophy, and I will quote, Kolmogorof's axiomatization is the usual formal theory, and the so-called interpretations of probability usually interpret it. So Hayek is not saying, Hayek's article mostly does take that point of view. He's the way he says this indicates that he's willing to think more broadly, but in fact, he doesn't have occasion to because he doesn't discuss game-theoretic probability in his article. Maybe we could persuade him to do that. Now, I think this advent of measure-theoretic probability, which was not there when, in the beginning of the 20th century with Pearson and Fisher, they didn't do measure-theoretic probability. Neyman didn't either, though he started, in order to get his paper on confidence intervals published, he started talking about it because people told him, hey, that's the new thing. If there's not enough new in your paper, but if you say that your paper uses measure-theoretic probability, it'll sound new and you can get it published. So since then, we've had measure-theoretic probability as the official religion of mathematical statistics, but it's not like, and that's had some influence. So what are some, and maybe it's not the only influence, but there's some strange things that happened in the 60s and 70s about the time that I was a student. One thing is the statisticians started calling these probability models or measures, they started calling their models data generating mechanisms. I have researched, tried to find, where did that start? It actually started, the first paper I could find it, what they meant by data generating mechanism was the accounting system that they were using. It was an article about naval logistics and how you priced things, or how, so that's how the data generating mechanism was actually, it really was a data generating mechanism. But since then, the term has been used more and more widely for a probability measure, like there was something creative about it. I don't know. That's the way a lot of people think about these probability measures. They're like, it's a kind of an ancient pagan idea that probability, chance creates the result. And about the same time, we had the philosopher David Lewis, who's very influential with many of the philosophers that have been participating, Barry in particular, participating in our seminar, speculated there might be some unknown, huge universal probability measure that constitutes the best description of reality over time. I think that idea couldn't have come along if we hadn't had this introduction of probability measures as somehow fundamental. And independently of that, the mathematicians themselves like to imagine some unimaginably huge, they added a filtration to it. So some unimaginably huge filtered probability space that describes all the trajectories of the universe. That's a kind of a folk idea among the mathematicians. But game-theoretic probability is something that can approach the problems more modestly. They don't have to imagine so much. A system of probabilistic predictions doesn't need to give probabilities to everything. And the kinds of predictions, if you take the game-theoretic point of view and to say a probabilistic prediction is anything you can bet on, it could be a single prize or it could be a one-sided prize, like what the imprecise probability people call upper or lower provisions. It could be a correlation. It doesn't have to be a whole probability distribution. And it can be anything that can be challenged by betting against it. And in that case, what is the interpretation? What's the natural meaning? Well, the first meaning is that it's going to have an objective meaning. It's going to be somehow correct or valid if by betting against it, you can't make a lot of money. That's the natural interpretation. And yet with that interpretation, we get the usual standard theory of probability. There's a, in terms of how much money you can make with a non-negative betting system, non-negative martingale produced by a betting system, that tells us what the probabilities are, or the upper and lower probabilities, if we want to get that. So you construct bigger things out of smaller predictions. I asked in one of our earlier panel discussions, Clark Gleamore was chatting before we started the panel. And I said that the philosophers hadn't been very interested in, I think I said to him that probably philosophers weren't very interested in game theory probability or something like that. And he said, well, the philosophers are not so interested in prediction, they're interested in explanation. Well, I'd like to put the thought in the back of your head that this game theory probability, in fact, does involve explanation, because you don't start with the whole thing. You don't start with a probability measure. Somehow, when you start with the whole probability measure, I guess you got something to explain, but that by itself doesn't seem like an explanation. Whereas a constructive process whereby you take a bunch of predictions and deduce some global conclusion from them, then that seems like an explanation. So the point is that the forecaster makes predictions step by step, round by round. And from those round by round predictions, you construct more global objects. Maybe it's a probability measure, maybe it's only an upper and lower probability or an upper and lower provision. And that constructive process is like an argument, it's like an explanation. To me, you can tell me why it isn't, if there's time in the discussion. So I wanted to ask the idea, maybe there is some explanation going on there. So we've had a lot of talk about physics in this seminar, which I've enjoyed. I've learned from it. I don't know as much about probability in physics as our other discussants, other panelists today. But I did bring to your attention these two recent papers, which give examples of how this game-theoretic probability process and prediction, how it works. One of them is a paper by Volodya and Yuri Gurevich, which talks about, negative probabilities, talks about kind of Wigner's idea and puts it in this betting framework, where, the negative probabilities don't really, they're part of a system that produces predictions, but they don't have, you don't make individual predictions based on negative probabilities. And then the other paper is by a doctoral student in Japan who wants to talk about, who's trying to tell us that you can do something analogous, at least, to these analogous to constructing the law of large numbers with the betting games. You can do something analogous to get the predictions of a Gibbs distribution without perhaps getting the distribution itself. So you don't think of that as a starting point, but as something that's produced as a consequence of the second law of thermodynamics. In the game-theoretic probability, the basic idea is that if the betting offers constitute a valid description, then you aren't going to be make money against them. And if I understand correctly, Mr. Hyura, the Japanese scholar, says that the proof, you can turn the proof of that into an argument that if the second law of thermodynamics holds, then you're going to get law of large numbers that you could alternatively deduce from the Gibbs distribution. So what do you make of that? I'm not proposing my own to go into that in detail. So let me summarize, but there it is. Let me summarize with my own slides if I can. So I can share my screen. I just have a slide to summarize what I said. So So here are, well, I was going to make it 3 slides, but my time is up anyway. So the first slide is the top. It says game theory probability produces the same conclusions with fewer assumptions. You don't need measurability or counterproductivity. You don't need probabilities for what the forecaster or the decision maker will do. The second slide says game theory probability is constructive. A decision maker fixes the conditions of observation. Forecaster makes betting offers, and skeptic selects which bets to accept. That's not just for quantum mechanics. That's what we do all the time. And then I give the example of quantum measurement from Wolfk and Gurevich's paper. So that's all I wanted to say. And I look forward to having everyone educate me today about whether any of this makes sense and how they like to think about it. Thank you.
Thanks so much, Glenn. Okay, and as usual, we'll move on to the next speaker, but I believe that many people have many questions. If you have any questions for Glenn or anyone else, please feel free to post them in the chat. Okay, so our next panelist is Dustin. Dustin, feel free to take it away.
Yeah, thank you very much. Yeah, my name is Dustin Lazarovici, as you said. Since last week, I'm actually no longer in Lausanne, but in Israel at the Technion in Haifa. That's also part of the reason why, unfortunately, I couldn't follow the this series until now, because I was too busy with stupid stuff like dealing with Israeli bureaucracy and so on. But I'm very happy and honored to be here now. And I also, in this round, suffer a little bit from imposter syndrome, because I feel like I'm still a beginner student when it comes to these game-theoretic approaches to probability. And so it's possible that some of my comments, in particular the more critical ones, are born out of ignorance. And then I'm very, very happy to be educated. But let me start by saying what I like about the game-theoretic approach. I like the fact that in some sense it's taking probability theory back to its historical roots, which of course were in dealing with gambling and games of luck. So I just like that aspect of it. I like that I think pedagogically or didactically it can be extremely helpful, because of course dealing with probability theory and statistics can be very difficult and counterintuitive, not only to students but even to many practitioners. And I feel like in many cases this game theoretic approach is more intuitive and easier to grasp. And I like many of the formulations of, I don't know, things like a p-value in this game theoretic terms. I think it can be very beneficial to students and practitioners. And then I very much agree with this insight that a probability measure often has too much structure, more structure than we actually need to explain statistical phenomena or to make rational decisions. That's something I very much agree with. Let me maybe try to express why I think I don't like the game theoretic approach so much when it comes to physics, or I should rather say the foundations of physics, which is what I'm mostly concerned with in my work. So explaining things like the second law of thermodynamics or the Born rule in quantum mechanics, etc. So first, philosophically, I don't like it that much because I feel like it's putting too much emphasis on a betting agent, like on the physicist as an agent. And I feel like, and again, I'm happy to be corrected if that's wrong, that it's putting a too anthropocentric perspective on physics. Of course, we are epistemic agents that want to understand nature, that want to explain physical phenomena. And of course, explanations and predictions have a psychological dimension to them, right? But I strongly feel like our beliefs, expectations, ignorance, and so on are insignificant to the course of nature. Right. I think, of course, not all of my colleagues agree with that. I mean, there are many approaches that are very clearly subjectivist approaches in statistical mechanics and physics that, in my view, are much more anthropocentric than the game theoretic framework. But still, I have this basic philosophical skepticism about putting too much emphasis on a betting agent. Then the second point is, I think, goes to what Glenn meant by explanations, that I can explain, that I can tell someone that however way she wants to bet against the second law of thermodynamics, she's going to lose, right? But I feel like this is not explaining why. It's not explaining why the second law of thermodynamics holds. And I understand, I think, in what sense Glenn says that there's an explanation involved, that we don't start with, you know, some full-blown probability law or probability measure, but we can approach it step by step with these betting games. But the kind of explanations that I'm interested in, I think, should be just statements about physical facts and physical laws, and as little else as possible. And I will, if I have time, sketch what kind of approach to probabilities in physics I think fulfills this kind of requirement of what I consider to be a good, satisfying explanation. And then the third point, deductively, I feel like the game theoretic approach is very helpful in dealing with uncertainty, right? Which is a lot of what probability theory does, but in my view, is not quite the point of probability when we get into the foundations of statistical mechanics, for instance. It's often to the contrary, the challenge, I think more so if I talk to philosophers, maybe less so if I talk to physicists, to explain that if we have, you know, let's say the probability of a significant decrease in entropy in a closed system is roughly of the order of e to the minus n, and the n is the number of the microscopic degrees of freedom in a macroscopic system, and so it's roughly of the order of 10 to the power of 24, so order of magnitude of Avogadro's constant, to explain that e to the minus 10 to the power of 24, how indistinguishable this improbability is from impossibility, right? So I feel that is more the issue than dealing with uncertainty, because in the end we have really, what we really want to explain and account for are laws of nature in every but the most metaphysical sense, that they are not fundamental laws. And this is, of course, the challenge, to explain how certain regularities, including statistical regularities, are grounded in the fundamental laws. Right? And I believe that these fundamental microscopic laws are deterministic, including in quantum mechanics, where I prefer the Bohmian formulation of quantum mechanics. And then we have certain regularities in the world, right? The regularity that entropy doesn't decrease in a closed system, or that the relative frequency of heads and tails in a long series of coin tosses is approximately 1/2. Or that the Born rule holds in a series of quantum measurements, right? And whether these regularities hold or not is in principle determined by the fundamental deterministic laws and initial conditions. And what explains these regularities and clarifies the relation between these empirical macroscopic regularities and the fundamental microscopic law is the fact that these regularities will obtain for nearly all possible initial conditions of a physical system, or in the last resort of the universe, possibly under certain macroscopic boundary conditions, right? Of course, if we care about coin toss statistics, we need to consider universes in which coins exist in the first place, etc. And this is what we describe in a certain approach to the foundations of statistical mechanics as typicality. There are certain macroscopic regularities that are typical, and that they hold for not just in our actual universe, but in nearly all possible universes, for nearly all possible initial conditions that the universe could have had. Right? And some of these typical regularities are statistical regularities. Right? For instance, the relative frequencies in coin tosses, or this is also the way I would think about Bohn's rule in quantum mechanics. Right? And then we do get probability measures describing these statistical regularities, like the Born distribution is a probability distribution, the Maxwellian distribution of an ideal, the velocity distribution of an ideal gas in equilibrium is a probability distribution. But those are probability distributions then of the unproblematic and intuitive kind, just describing typical statistical regularities. They have nothing to do with knowledge or belief or uncertainty or anything like that, right? So for instance, if we look at an ideal gas in a box, right, then for almost all possible microscopic configurations that the gas could have, we find that the velocities of the gas particles are approximately distributed according to the Maxwellian or Maxwell-Boltzmann distribution. And this distribution is just an empirical distribution telling us approximately what fraction of particles will be found with a velocity in this and that interval. So in the unproblematic sense. And of course, to explain what we mean by typical, by almost all initial conditions, we usually employ a measure. Often it happens to be a normalized measure, so technically a probability measure, but it's clear that we don't need the full structure of a probability measure, right? We just want to say what obtains for the vast majority of possible states or possible initial conditions of the physical system, or in the last resort, on the most fundamental level of the universe. And I think that this captures this concept of typicality. And I should say that the rationality principle that goes hand in hand with typicality, why I think that these typicality statements that some regularity holds for nearly all possible initial conditions is predictive and explanatory, is a form of Cournot's principle, right? About which I've learned more from Glenn than from almost anybody else. Although this Cournot principle in this sense is tied to something a bit different and weaker than probability, right? It's just saying that if something obtains for an overwhelming majority of possible initial conditions, or an overwhelming majority of possible worlds allowed by the fundamental laws of nature, then we can regard it as morally certain, so to speak. Practical certainty sounds almost too weak in this context, right? And I feel like this does explain why on the fundamental level, we need much less than a probability measure, right? Because we don't need to assign probabilities to any set or any measurable set of possible initial conditions of the universe. And I think it provides the kind of account, the kind of explanation that I'm satisfied with, in the sense that it is really a statement about the physical laws, right? It is a state. So certain regularities are explained by the fact that there are the kind of regularities that the fundamental microscopic laws will bring about for nearly all possible initial conditions. And so this is for me a statement really about the physical laws that doesn't involve knowledge, belief, ignorance. And that fits well with my view that we ultimately as epistemic agents are rather insignificant to the course of nature and to whether or not the Born rule holds or whether or not the second law of thermodynamics holds. So
Okay, Dustin, I think you're out of time.
I'm done too. Thank you.
Okay, thank you so much. Yeah. Is this? Sorry, are you finished? Did I cut you off?
No, it's a good point to finish.
Oh,
Thank
okay. Thank you so much. Barry has already raised some questions in the chat, so people can take a look. In the meantime, thank you so much, Dustin, for the discussion. And let's move on to Leah. Leah? Hi, Leah. Okay, feel free to take it away whenever you're ready.
Leah needs to unmute.
Okay, can you hear me now?
Yes, we can hear you.
Okay, I'm not looking at my own screen in a very good way right now. Hang on a minute.
So we can see the slides.
Can you see them in full screen?
No, we can't. We're seeing.
Okay. Yeah. I had this right just before we began, and now it's.
If you push the, there's a little icon down at the bottom
Yeah.
for a PowerPoint.
Okay, let me try this. Now.
The icon is down at the bottom. Well, okay.
Okay,
Is this working now?
Yes, this
Yes.
is perfect.
Okay. Yeah, so well, thanks very much for having me here. And I find this whole approach to probability quite intriguing also, and in particular in relation to quantum theory. So that's what I want to sort of to focus on in these comments. So I guess the main thing I want to do is sort of perhaps just sort of sketch out how I see the sort of lay of the land in terms of different interpretations of quantum theory and the way they deploy probabilities. And I think maybe along the way point to a few sort of points of connection, I think, between this idea of game-theoretic probability and things that are already happening in foundations of quantum theory. I think one of the things that's most intriguing about it actually is that it does, so Dustin was not very keen on this, but and in fact what I'm going to talk about is how there is a bit of a split, I think, between different people in the foundations community over how they feel about having observing agents involved. And so this is, oh, hang on. Yeah, there we go. So there is a kind of, I think, long-standing divide in quantum interpretations between, so those on what I've got on the left here, who are more inclined to think that quantum mechanics sort of perhaps even requires us to involve an observer in a fundamental way. And those on the right who take more the kind of attitude that that Dustin was just sketching, where that's not what a physical theory ought to be about. And I think this divide in some ways goes right back to some of the early formulations of quantum theory. The Copenhagen interpretation, for example, developed more out of the sort of formulation in terms of matrix mechanics. Whereas I think you can trace some of these more observer-free interpretations to the to the sort of wave mechanics side of the way the theory was formulated in the early days. So let's look at the sorts of cryptic statements that Copenhagenists made in the early days. So Heisenberg said, the idea of an objective real world whose smallest parts exist objectively in the same sense as stones or trees exist independently of whether or not we observe them is impossible. We had Bohr saying evidence obtained under different experimental conditions cannot be comprehended within a single picture, but must be regarded as complementary in the sense that only the totality of phenomena exhausts the possible information about the objects. So these early sort of ideas about the Copenhagen type interpretation did place the observer as sort of ineliminable. And that's in some sense, the point of view from that school has always was that that's a sort of conclusion that's forced upon us by quantum mechanics. That's as I had here the message of the quantum, that that this is what this theory is telling us. But of course, there's like strong resistance from the other side, which goes back to Einstein. And Einstein was very unhappy with the theory and thought that it violated what he saw as the programmatic aim of all physics, the complete description of any individual real situation as it supposedly exists independent of any act of observation or substantiation. And that kind of line of that kind of Einsteinian way of thinking, you know, comes through in the what I had on the right-hand side, interpretations like de Broglie-Bohm, spontaneous collapse theories, Everett interpretations, where the aim is seen as, you know, providing an ontology, providing a dynamics for a theory, not messing around with these observers having any part, but trying to like figure out how to get a decent picture of what's actually going on in reality, despite the fact that and this is what's awkward about quantum mechanics, that in at least sort of classic textbook type formulations of the theory, if you look, you know, a bunch of the postulates involve measurement. And so this is awkward if you're trying to get rid of observers and measurements and things like that. And so, you know, these interpretations try to build up an ontology and sort of either somehow find a way to explain away or accommodate these last three postulates, which all do deal with measurements and observers and things like that. And in particular, of course, the particular form that probability assignments take in quantum theory as given by the Born rule. So I think, no, Barry, I'm sure surely would say more about this, I think, but I think it's fair to say that de Broglie-Bohm and spontaneous collapse, so looking at these sort of observer-free type interpretations, they usually, those two at least usually appeal to sort of more objectivist notions of probability, and there's different options there. The Everett interpretation also I've sort of put it on that side, though because it only sort of allows itself in some sense, the first two postulates. It wants the state to be represented by a wave function, and then the Schrödinger evolution of that. It gives itself a bit of a problem with probabilities. And interestingly, and I think this is one of the places where there is something similar going on to the game-theoretic ideas, In order to, so let me just first of all quickly say why they give themselves a problem is because they have a sort of branching wave function. And according to that interpretation, that's all there is. And then you have the problem, well, how do we get back the Born probabilities? Why should we actually get probabilities that conform to the Born rule? And so what's been tried is to give a sort of decision, what they call decision theoretic, but actually in the original formulation by David Deutsch, it was quite game theoretic. That involved, an observer playing against nature, and it was quite similar in the setup, at least, to what Glenn has suggested. And so to try to recover the probabilistic part of the theory from a sort of game/decision theoretic foundation. Now, on the other side of the divide, so those are all the sorts of interpretations which perhaps go together with the kind of mindset that Dustin expressed. On the other side, we have these more sort of epistemic interpretations, which are not so adverse to involving an observer. And here again, I think there are some places where there could be some connection to this idea of game theoretic probability. So there are different sort of streams within the epistemic interpretations. One of them is cubism, which originally meant was an acronym for quantum Bayesianism. But Chris Fuchs, its founder, later changed its name to quantum betabilitarianism. And that's a sort of nod to the pragmatists, the American pragmatists, and in particular to Oliver Wendell Holmes, who said, I describe myself as a betabilitarian. I believe that we can bet on the behavior of the universe in its contact with us. We bet that we can know what it will be. So this idea that from a sort of pragmatist point of view, you're not necessarily looking for a representation of the world completely independent of what you do with it, but that you're looking for a theory which allows you to best go on with the world, to bet on it, to get things right about it. So I think this is an interesting point of contact. Other epistemic type interpretations also look to sort of generalized ideas of probability. So I'll just give a couple of examples. So there is a sort of school of information theoretic interpretations, which came from Jeff Boob, and now has been taken up in a new book by 3 Michaels. So Jeff Boob originally sort of suggested an analogy to special relativity, saying, well, look, that provided a sort of new theory of space-time, where the space-time had a different structure than Newtonian space-time. And his idea is that quantum theory provides a sort of new theory of probability with a different structure than classical probability. And so then the task, of course, is to explore what that new theory would look like, what that kind of concept would look like. And this is also a theme in this sort of long-standing and ongoing reaxiomatization program for quantum theory, which tries to sort of use a framework of generalized probability theory, which takes a very operational approach to the quantum, to the state, to measurements that you can make and things you can do to the system, and tries to basically locate different quantum theory in a sort of broader landscape of probability theory, so that it appears as one kind of probability theory. Classical probability theory appears as another. And so, yeah, so I guess in relation to, so I think, so the idea of game-theoretic probability is interesting because in this kind of space of the interpretational landscape, if you like, people are trying to find some kind of middle ground between, you know, very subjectivist interpretations of probability and very objectivist interpretations of probability. So I do wonder whether this is the kind of place where it, you know, could be brought into dialogue with other existing approaches. I think that the idea that Glenn sketched of the experimenter in dialogue with the quantum world, who sort of gives the answer, that sort of framework is sort of amenable here. But I think that, like, what people would be looking for, the sort of interpretational task in this part of quantum interpretation, is to also get an explanation out of the interpretation for why exactly quantum theory takes the exact form that it does. So you want to explain, as I said before, why the Born rule looks like this. Why is there a way to capture what the physical requirements are, which make it the case that this is the form of the Born rule. And so I think that's the sort of extra development that would be sort of expected from any sort of proposed, you know, generalization of probability in this domain. Would be people are exploring the idea of, you know, taking more general approaches to probability, but then you also need an account of why quantum mechanics is the particular kind of theory that it is within the broader landscape of possibilities. Yeah, so that's pretty much all I had to say. I'm not sure how long I took there, but
you're right on time. Thank you so much. Yeah, it's wonderful. And okay, again, I think many people might have many questions, so we'll delay till the end. And we have our last panelist, Eddy from UC San Diego. And Eddy, feel free to take it away.
All right. Can you hear me? Can you see my slides, my notes?
Yes, perfect.
Great, thank you. Well, it's a great pleasure to be back in the Foundations of Probability seminar. It's great to see you all. And I want to give some brief comments on game-theoretic probability, since I'm the last speaker, so I hope to keep it short. So I remember correctly, I think this is the topic of the first talk Glenn gave in the Rutgers philosophy department. I think it was organized by Brandon Feidelson with a bunch of graduate students in a small seminar room. The first year we moved to the new building. So I remember vividly of that talk, and remembering Glenn drawing a picture on the whiteboard with the trees, ever-growing trees from one side to the other. So it's very fun. And in the last 5 years, I had the pleasure of attending many of the seminars lectures and seminar, including ones by Glenn and his collaborators on this topic, and in connection to game-theoretic probability and p-values, risk and uncertainty, finance and communication with statistical results, and wider applications, say, to things like physics. So my goal today will be to discuss the connection between game-theoretic probability and physics, and with the proviso that my knowledge of this area of probability is very limited. So I only got this knowledge from cursory reading of the texts, but I want to learn more from Glenn and others. So right now, given my very limited knowledge, I think the upshot is this, that the game-theoretic probability is more suitable as a methodological foundation rather than a metaphysical foundation for physical theories. So this is much in agreement with Dustin's conclusion earlier. Okay, so here's some philosophy of physics to keep in the background, or to borrow a term from Barry and David Albert, architecture of fundamental physical theory. So we have at the bottom a fundamental ontology of matter in space-time. Okay, so what exists? And there are also fundamental laws of nature that govern or describe the fundamental matter in space-time. So dynamical laws of temporal evolution, say F equals ma, the Schrodinger equation, constraint laws, Einstein field equations, the past hypothesis that constrain the fundamental possibilities of this space-time. There are two views on the laws that govern or describe. One is a Humeanism, the view in which laws merely describe reality in some kind of efficient way. And there are varieties of different kinds of humanism. There's objective humanism, the Lewis humanism, the Barry kind of package deal version of humanism. There's the pragmatic humanism, and so on and so forth. Some version of this may be more friendly towards the game-theoretic view. There's also non-humanism, which I endorse. I endorse a particular minimal version of non-humanism in which laws govern not by evolving things forward in time or producing things forward in time, but by constraining the whole damn thing altogether, right? So here's a minimal block, the space-time block, 4-dimensional. All there is, past, present, future, are some parts of this block. So here we are talking about this, and the laws govern the whole thing altogether. So, for example, modeling might have the view that laws govern by producing things from T1 to T2 to T3 and forward. This kind of productive sequential development. But my view is much more minimal. I call this MIMP in a paper written with Sheldon Goldstein, minimal primitivism or minimal non-humanism. Okay, so in my view, there's a whole block, but there's no arrow. There's no, we don't commit to a fundamental distinction between past and future or a direction of time. And this is important to Glenn's project too, I think, which I'll come to later. Okay, now, so the mental imagery we have here is that this views on laws, ontology, and metaphysics is compatible with it being a 4-dimensional block universe in which observers and agents are not fundamental in this architecture. Okay. But of course, it's not the only philosophy of physics one can endorse, like Leah mentioned. There are people like quantum Bayesians and others who much more embrace centrality of agents, and perhaps more in a dynamical universe too. So on this picture, how to fit in probabilistic views, probabilistic laws is controversial. Are probabilistic laws scientifically fundamental? If so, how do they govern the universe? Or how do they optimally describe the universe? In what way do they describe in an efficient way? Are probabilistic laws universal laws or partial descriptions of local matters, only particular descriptions of some substances and construct them forward in globally? But they are primarily, are they universal or very, very much local? And what do probabilities mean in the physical laws? Are they subjective or objective or both? And are the probability measures given all at once or from a temporal point of view, or are they given to agents round by round, step by step, as Glenn has put it in the notes? And how should we think about the direction of time in probabilistic laws? Are they only transition probabilities, say from T1 to T2, the probability is 1/3, some outcome O? Or are they something like there is no fundamental direction of time that can be applied forward and backward? You can extrapolate probabilities from T2 to T1. Okay, so lots of issues here. Now, there are also methodological issues about how should we test physical theories and how should we extract statistical predictions from physical theories. So testing and making predictions from physical theories. I think the metaphysical issues are logically independent, distinct from the methodological issues. So how should we test a physical theory? Should be independent from what physical theory means. like what kind of things is described in the physical world. And for the game theory probability, I think the picture is suitable for physics depends on how it is applied. Is applying to be part of the methodological foundation is a simple way of understanding prediction and testing physical theories. Or is it being applied as part of the metaphysical foundation as a component of fundamental physical theory interpreted as fundamental probabilistic laws as a key part or ingredient or variables, the fundamental laws? Okay, so I think the question will turn on whether we're meaning in this application or this application. So the main option is this is fine, and this is, I think, not so clear. And I think that there are reasons to push back on putting game-theoretic probability in the foundations of physics, metaphysical foundations of physics. Okay, just to give a summary of how I understand game-theoretic probability. So it is primarily about perfect information games, right? So players move in turn and see each other's moves as they play. So I take this from one of Glenn's Q&A interviews posted on his website. So you have 4 agents, 4 players: forecaster, placing bets; skeptic, rejecting or taking bets; reality, playing kind of objective role of determining the game. So one example from finance is that the forecaster is a trader trying to make money, multiply his or her capital. The skeptic is the larger market. And the reality is still the larger market, or maybe the entire world. It includes the market and planets and stars and so on. Okay. So the hypothesis here is that the trader will not multiply their money by a large factor relative to some market index. This will not happen. It's almost like a version of Cournot's principle, if I understand correctly. And if a trader multiplies their money by a large factor, then the market efficiency is called into question. Okay. So how should we apply these similar ideas to physics? There's one example from Glenn's slides on quantum measurement. I didn't understand that scheme, so I'm going to use my own scheme here. Probably mistaken, but let me know if it's wrong. So here is a very simple-minded model for applying game-theoretic probability to physics. So a forecaster is a scientist trying to confirm or disconfirm a physical theory. So I'm doing experiments, theorizing, and trying to make some announcement, prediction, and trying to confirm, disconfirm physical theory. A skeptic is a physical theory. Reality is the universe or nature. So 3 players here: a scientist, physical theory, and the universe. Think about, say, Giancarlo Girardi, who is doing GRW theory, or Angelo Bassi testing GRW theory as a forecaster. And skeptic would be the GRW theory itself, the reality being the universe, right? The hypothesis is that a scientist will not observe atypical results relative to some property in some kind of long-term, a sequential measurements, right? And if a scientist observes atypical results, the theory is called into question. Time for a new theory, or time for twisting the theory somehow, twisting parameters, adjusting the variables, or making it a new theory. We reject the theory. So here are some features of this very simple-minded model. See, the role of observers is quite central here. It is one of the 3 components, one of the 3 players in the game-theoretic model here. The duration of time is present here too. That is, you do this sequentially, and you do this probability to future outcome, future predictions. So it's pretty fundamental here. Discrete time, offers made step by step, round by round. It's not continuous time, it's discrete time. Constructive, from the round by round ingredients to more global objects. So probability measure is not given all at once, and certainly not atemporal. So the measure that we get from a physical theory is not the one that's over all possible histories, trajectories, histories of the universe, but something more like, for this particular context, this measurement at this operator, you're going to have this possible outcomes and what the probabilities or the frequency we're going to expect. So in this sense, I think that game theory probability is more suitable as a methodological foundation for prediction and testing in physics than part of the metaphysical foundation for probabilistic laws. Because this is not quite how we understand, say, a genuine probabilistic law in GRW, Chen's law, stochastic mechanics, stochastic dynamics. But it may be a simple way to present how we should test, how we should present the statistical results to the wider population. That is, we are doing this kind of thing as if we're betting against some kind of theory. And reality is going to set who wins the bet. Now, if we consider this as part of the metaphysical foundation of physical theories, then it might be a non-starter for those who do not want to commit to a fundamental direction of time, for those who do not want to have to rule out continuous time in probabilistic laws, for those who want to have universal probabilistic law that apply to the universe and complete theory, histories, and for those who want to minimize or eliminate the role of agents, and for those who want to explain why certain bet is a good bet, explain, not just predict, right? For all those people, such a picture might be a non-starter for the metaphysical foundation. However, it may be better for, and this might be agreeing with Leah's slides on the other tradition in philosophy of physics, quantum mechanics, better for those who want to accept discreteness of time for independent reasons, but also allow discreteness to be on the human scale, not just on the Planck scale, but something like on the human scale. Those who content to think of physical theories as tools and instruments only for making predictions for us. Instrumentalism, or kind of broadly instrumentalist taking on philosophy of physics. And for those who want to embrace the generality of agents, who might be motivated by quantum mechanics already, to think that agents are central and dynamic components of how the universe works. And for those who are okay to place physics on a normative foundation, such as Healy. So Healy wants to propose that we should replace descriptive facts with normative facts, such as what we ought to expect as the foundation of physics, not what there is. So in his recent book, The Quantum Revolution in Philosophy, he argues that the fundamental facts should include things like what we ought to expect, and should not include things like what there is, or not only things like what there is. But this does not diminish the significance of game theory probability. It may have much to teach us regarding how we should test physical theories, how to extract their predictions, how to communicate statistical results of physics to non-cyclists. Okay, so that concludes my brief comments on game theory probability and physics. Okay, thank you all.
Thanks so much, and thanks again to all the panelists for wonderful, wonderful presentations. So we already have many comments in the chat by Glenn, Barry, Marshall, and I'm probably missing someone. So maybe, given that Glenn is one of the panelists here, and this is on game-theoretic probability, maybe Glenn, you can say something to start us on the discussion. Glenn, you are muted.
So I want to thank Eddy and Dustin and Leah for their thoughtful. This is really, I think of all our panel discussions, this is one where people really have on some of the same questions and not talk past each other. So I'm very flattered and honored by your efforts to make some sense out of this. I would say, I think I agree with what Eddy was saying in spirit. I put in the chat some corrections. The forecaster, if we're thinking about who's testing the theory, it's the skeptic who's testing it. The forecaster is stating the theory. In the case of a theory, the forecaster could be stating his own opinions. The forecaster, if it's a weather forecaster, they're not doing a fundamental physical theory, they're just using a models. But the forecaster, whatever theory we have, is the forecaster stating it and in a sense constructing it. The skeptic is trying to bet against it to refute it, and in that sense they're working together maybe to find a good theory. skeptic is doing the testing of the theory. Well, we could say more about that. So when Eddy means atemporal, I think he means we have a sequence of time. He's assuming that it's just the direction of time that is not. When he says atemporal, I think he means just, is that right, Eddy? That atemporal just means that we haven't decided which direction time goes, not that we could mix things up.
I meant something stronger. I meant atemporal in the sense of there is the block universe. So all there is in the kind of four-dimensional space-time. And of course, that's also compatible with there being no fundamental direction of time.
Well, certainly if you're going to have probability, then you need to have if you're going to look at one sort of one particle after another or something, you've got to have them ordered in order, because if you have an infinite sequence of zeros.
Right, there's ordering, right.
Yeah, so you have
so
ordering.
Between is ordering, for example, that which is between which. Yes.
Okay. I just wanted to, I understood that. I thought that was what you were doing, but the word atemporal could be confusing there.
I see.
What else did I want to say about, I think one of the things that I have felt I learned from game-theoretic probability from really Volodya-Vovsk, he brought these protocols, these game protocols from machine learning, or maybe he just invented them himself, I don't know. But the marvelous thing about that is that you see there are these different roles. The forecaster and the skeptic and decision maker is a third role that we have in, some examples. But these different roles, are really doing different things. And often in the Bayesian context, it looks like there's just one, it's like a one-player game, where it's just the one player against reality. But here we have the forecaster and the skeptic, and they're doing different things. So what is objective? So it's not like we're talking about subjective probabilities. We're supposing that there's some objective probabilities given by the physical theory. And we're testing those objective probabilities. Or maybe we don't even quite know all the objective probabilities. We might be only seeing some aspects of them. And we're using that to test the physical theory. So it's not quite in the same subjective league as a Bayesian model. I don't know that anyone said anything to contradict that, but I wanted to clarify that there's a sense of objectivity here. And so, you don't have to have, well, in quantum mechanics, you've got the decision maker that decides. But I fully accept the Bohmian view that puts the experimenter in the wave function. Okay, but that's not a part of what we could test clearly. But we could still test it with as Eddy says, with the game-theoretic approach. But there should be some this methodologic. I put in the chat this distinction between that. I forget who wrote the article. There's an article on certainty in the 17th century French encyclopédie. And I forget, or I haven't looked up whether that article was written by D'Alembert or by Diderot. And I was trying to guess when I was writing in the chat, I was guessing it was D'Alembert. So whoever it was, say D'Alembert, had three kinds of certainty: moral, physical, and metaphysical. And physical certainty was, moral certainty was like you're sure of it because everybody told you it's true. Physical certainty is like, if you see your hand burning, you know your hand is burning. That's their example. Metaphysical certainty is like mathematics, right? So It sounds like I was saying we need a terminology like that. I wrote in the chat, we need some terminology like that today. People don't if they say physical nowadays, the meaning of physical has changed to be metaphysical. So we need some distinction now that we could use, and Eddy proposes it, methodological and metaphysical. I'd be curious as to whether the other philosophers of physics would accept that metaphysical, because I think there's still, metaphysical still has a negative connotation in some places in science. But I would be happy with it. Yours is metaphysical. Whereas, so, okay, we want a metaphysical level of explanation, but that involves possible worlds. It's not all just about our world. Whereas if we're talking about our world, then what Eddy is calling methodological is all there is. So I don't know what, maybe that's enough for me to say at this point.
Repeat, how did you characterize moral certainty, or how did the encyclopedia characterize moral certainty?
Well, they give an example. The example was that if somebody tells you that the governor just did something, and everybody says it, they all report it, they couldn't all be lying. So that's moral certainty. Whereas physical certainty was something that you experience with your own senses in a very, he uses the example of your hand, fire in your hand is the way he said it, fire on your hand. No, you don't make any mistake about that. You know. Whereas metaphysical, he uses the example of 2 + 2 = 4 or something like that, a mathematical truth.
Interesting. Yeah, I feel like the notion of moral certainty certainly has undergone a lot of transformations. So I mean by moral certainty basically what falls epsilon short of absolute metaphysical certainty. So what would be absurd to doubt, even though doubt is logically possible?
Yeah, there's that would be more like, you know, Cournot, by the time this was 18th century, a century later, Cournot was using physical certainty, was using the term physical certainty, as you know, by what you're calling what you know, in that working paper, I've been translating moral certainty by practical certainty. But I kind of like physical.
Right. Yeah. Well, it's problematic about Cournot that he speaks about he speaks about physical impossibility, which.
Yeah. I think he's following. I think he's using it in his sense as he thinks he's using the meaning that was given in the encyclopedia, I think. I would suppose. It was not something he invented. It would be a sort of natural, authoritative, the way French was used, educated French was used at his time.
Mm.
So is it right, Glenn, just to clarify on the comments you made just now, on the application of game-theoretic probability physics, that is, you are okay with it not applying to the metaphysical foundations of physics, say as the genuine explication of chance or probability in Bohr mechanics, but something more like how we test, how we use physical theories.
Well, I guess I'm something of a, I don't know what you want to label me as, a philosopher, a positivist or something, but I think this metaphysical is, I'm not so crazy about metaphysics. So I'm happy. But I think it's more than methodological. It's really all there is as far as our own world is concerned. And it's a kind of a law too. It's a kind of a law. It's not just, you know, our belief, and it refers to not just to the testing that an individual can do, but to the testing that you could imagine anybody doing. Cournot had this idea of some demigod who was doing the testing, just like just like Laplace's superior intelligence. So it is something that's a little bit beyond, but it's kind of an idealization of human agency, if you will. So it goes a little bit beyond.
But I think it's very much related to Barry's question, whether the game theoretic approach gives an answer to the question, what features of reality make probability statements true? Or would you say that
this is a feature of reality, is all that any testing that could possibly be done is a feature of reality.
Yeah, I think my feeling
Tell us
is
about
that by bringing in the other characters in the game, like skeptic, or you also had experimenter in one, they provide the role of, picking a particular measurement to perform in some of these things. And once you've got that with the quantum theory, then you've got everything just like normal. So it's sort of in the sense that, once you've, this is the sort of Copenhagen idea, right? Once you've defined what you're measuring, then you're good, right? And you've got a sort of, and so if you've got a way to sort of bring in that choice as part of the foundation of probability, rather than having to sort of just put it in there for the reason that quantum mechanics forced you to, then I think that gives you a different perspective, right? It gives you the perspective that if you go with the more general picture of probability, then the specific case of quantum mechanics kind of falls out rather than it being the other way around.
I like that comment. Yeah, it is. This is what probability is like. Yeah.
Barry, do you have a word on this or something else?
Well, I do want to make a remark about what Glenn said. I think what he said made very clear what a lot of the difficulties have been in communicating across a bridge. Of course, to philosophers of science now, metaphysical doesn't mean Hegel or whatever the positivists were reacting against, or Bradley or McTaggart. What it means is answering a question about what is it in the world that makes claims true or false, as Dustin said. And I don't see that what you gave what game theoretic probability might be doing is giving an account of how we find out what probability claims to assert or not assert. But it doesn't say what are the fundamental features in reality that make these claims right or wrong. I found it immensely difficult to get this distinction across. And sometimes I've wondered, maybe there isn't a distinction. Maybe I've wasted my whole life. Okay, but I don't think so.
It's not just, there's a little more, as I was saying just now, Barry, there's a little more than how we find out or how I find out. It's sort of like Laplace's superior intelligence. It's a limit of what could be achieved, just like Laplace's physical laws.
Yes, well, there's an account of what probability distribution corresponds to what Cournot calls the I don't know what I forget the exact words he used, but what a demon who wasn't quite Laplace's, but who was going to give information to human beings. They would give information by using probabilities and facts about the world as to what, right? That our world is such that there isn't a unique probability distribution. And maybe if the demon told people about what's typical or not, it would be doing better. That's a dispute between me and Dustin, maybe, but it's still an answer. Dustin is still giving an answer to the question that I think philosophers are interested in.
Well,
or at least I'm interested.
Would you consider Laplace a well? Steven Stigler was made fun of me for talking as if Laplace were a philosopher.
Oh no, I think he was. I think he was a philosopher in part, of course. He was a
So was
mathematician and-
was his notion of a superior intelligence, thinking about physical laws in that sense, that had, he had that notion in there, that superior intelligence was.
He had a notion, it's right. He was
Yeah.
saying what he thought determinism was. In fact, the famous quote is actually not, what he said actually isn't right, because he didn't really say right what the superior intelligence has to, what information have to supply to use the laws. But I'm sure Laplace knew what to say, just the quotes didn't have it right. But he was trying to explain what determinism amounts to. And that's right. But it also is that even if the laws were deterministic, as came up last time, it might be that we can still, just knowing the deterministic laws on their own doesn't tell you very much about what's going to happen. But knowing what typically happens or what the probability distribution is, together with the deterministic laws, will tell you a lot.
Yeah, I mean, I don't disagree with that, I don't think, but I'm just saying that in Laplace's time, it made sense to people that you would describe the fundamental structure of the universe, which you thought was explanatory, still using the concept of a superior intelligence.
Yeah, sure.
So this is doing the same thing.
So you're agreeing that it's not answering what I'm saying is at least what you're calling, I think, somewhat pejoratively, the metaphysical question.
If metaphysical question has something to do with other worlds than our own, then yeah, that's right.
I didn't hear the last word, but I'm going to shut up.
I'm saying if metaphysical means that you're not just talking about our world, but other worlds.
No, it doesn't.
Oh.
As Marshall said in the comment, possible worlds are introduced in order to say things about the actual world.
Well, I think this point of view doesn't require that. Yeah.
Maybe.
Marshall, would you like to comment on this or?
Yeah. So Glenn, it sounds like this was a really helpful discussion for me in understanding your view. It sounds like your view is that whether or not skeptic were to bet, there would be a fact of the matter about whether skeptic would be able to make lots of money. And nothing, so in the way in which you're positivist like, it sounds like, is that nothing deeper explains that fact. But nevertheless, it's a fact about the world that skeptic would not be able to make a lot of money if forecaster and reality are set up the right way. Which, by the way, is a counterfactual statement. So involves possible worlds potentially. But it's a statement about our world, that our world is such that skeptic can't make lots of money. Is that a fair characterization?
Yes.
Okay, yeah. That's really helpful.
Or you could say, yes. I mean, you can also replace the player skeptic with a battery of actual strategies for skeptic.
Sure.
That makes it maybe sound a little less counterfactual.
Okay. Yeah.
They'd be the simple strategies somehow, sufficiently simple strategies. Yeah.
Thanks.
Can I ask, and I'm now saying things that are philosophically not quite correct, but in some sense, Barry's view would be that the answers that reality gives, not just to actual measurements, but to anything you could ask about the world, right? They ultimately determine what the true probability law is. In this what is it in this game theoretic account? There's something over and above reality's answers that sort of determines the right or the reasonable probability distribution, right?
Would you repeat that last sentence?
Yeah, there's something
in whose view? In whose view there's something?
In the game theoretic view, there's something other or more than reality's answers that determines the right probability laws or probability distributions, if there are any.
Well, why did you think that?
Was it not?
Well, I'm not sure I agree with it. No, I don't know why I need to say that. Maybe you saw some reason I have to say that.
No, I think that it does depend on the forecaster and the skeptic in a more.
But forecaster is. I mean, we can replace forecaster by the theory, and then we can replace skeptic by, as I said to Marshall, a battery of tests. Skeptic is not there anymore, and forecaster is just theory. And the question is, does the theory fit reality? That is then the question. And I think reality is all, I claim credit in my conversations with Volodya 25 years ago. I claim credit for calling this player reality instead of nature. Because if we called him nature, we would have said, oh, we're talking about some laws. No, we're just talking about that is what it is. So it's kind of a Humean attitude in that. Yeah, reality is just what reality is. That's it. And maybe, I mean, this leaves open. Yeah, okay. Then is there a good probability distribution that describes everything? That's a scientific question, I guess, which really be answered entirely. Yeah.
Can I ask a follow-up question on this?
Sorry.
Is reality so inclusive that includes also the skeptic?
Well,
that is the skeptic
yes
part
and
of
no.
reality?
Yes and no. I mean, you can make it, can't you? You can have one skeptic testing another skeptic.
But are they both in reality in the sense they are real skeptics?
Well,
they're not kind of factual skeptics.
You could replace skeptic by a battery of tests.
Then they are in reality.
Well, they're not in the game anymore. If you have a game and you assign one player a strategy, basically you eliminated that player from the game. They're not in the story anymore. It's because you've kind of mathematically taken them out.
Thinking metaphysically, anything in the world is part of reality, right? So if a skeptic being a person or a sequence of tests, they got to be in reality.
Okay.
So should we think of ultimately in physics, there are only two players, the theory and the world.
Okay. Okay.
And the theory in a sense will be kind of candidate for the best system. In the game theory point of view, you can think of the systems involving not global distribution over all possible worlds, but some more localized distributions or localized probabilities that given round by round time dependently. So you can basically think of the forecasters that being different systems we evaluate, reality being the one that chooses which one is the best.
Yes, I think that's right.
That would be a way to reconcile humanism or best system account of laws, or kind of pragmatic best system account with game theory probability, in the sense that humanism itself does not privilege that global universal distributions over localized distributions. You can also talk about all kinds of theoretical terms as long as they're useful in describing the actual world.
But you lost skeptic. You lost skeptic. Maybe
you lost a skeptic because it's part of the mosaic.
But people, I mean, the problem is games are very flexible. You can use this, we're talking about how you use this framework for theoretical physics or something. But as you said, you can use it for experimental physics, when you can also use it for weather forecasting. You can, so the framework is infinitely pliable. And you can put other players in. In some of the games in our books, we have more than 3 players. We have more than 4 players. You know, you're not, you can't say, I mean, measure theory has a certain, it isn't really true, but the official story is that measure theory is just, there's one set of axioms, that's it. You never vary them. It's not really quite true. You define these filtrations, and martingales are defined in different ways. But with game theory, it's clearly not true. It's, you know, because you show me a game, I can make a variation on it. I can make a different game. And a lot of the mathematical structure that we find in this game, in our book, for example, Francesco, who was here earlier, has got a slightly different version for prediction. You get into the kinds of things people are doing in machine learning. Yeah.
Isn't one upshot that metaphysically you could be a Humean if you were interested in metaphysics?
Yeah, I guess I'm quite sympathetic with it. Yeah, that's right.
Or it can be a non-Humean to think that forecasters are non-Humean laws that govern.
I could be, yeah. I mean, it's sort of like, yes. It's not my, I guess I don't really have a dog in that race. It's true. If I weren't 75, you know, I might become a philosopher. And,
Can I ask? You mentioned as one of the virtues of the game theoretic account that it doesn't rely on measurability. I never quite encountered measurability as an issue. I mean, if you do like mathematical physics, statistical mechanics, that's rarely the kind of problem that you encounter, you know, whether a function is measurable or whether a set is measurable. Is it in other contexts such a big obstacle?
oh, I think the pure mathematicians, if they wanted to take what you're doing and make it quote unquote rigorous, they would start introducing assumptions that say things are measurable.
Yeah, sure. But are these assumptions problematic?
Are they problematic? Well, they're just a distraction. Kolmogorov's explanation was we add these assumptions in order to make our rigorous pure mathematics work. And they're not going to be a problem because we never could, you know, we're never going to, countable additivity said it's not a problem because we'll never see an infinite number of sets. And measurability is not a problem because we'll never see a non-measurable set. So somehow it's a certain amount of nonsense that we don't have to start with. Now, I should make it a caveat though. In the 2019 book, Volodya added some continuous time things. And to make to do probably in continuous time, game theoretic or measure theoretic, you need measurability. Non-standard analysis. In our 2001 book, we use non-standard analysis. That's another way of doing it. But that's kind of metaphysical too, isn't it?
It's just usually you like in mathematical physics, you make many idealizations, simplifying assumptions that could be questioned, but I never encountered someone objecting to the assumption, let f be a measurable function. You know, it sounds rather harmless for the reasons that you.
But you say it. You're enough of you're forced to be mathematical enough that you've got to say that. You've got to say it's measurable.
Yeah.
Well, I would ask whether once you say that you start with one measurable thing and you do a bunch of other stuff with it, have you really checked that you still have measurable things? The mathematician picking at your work might have some questions. Possibly.
Okay, I see.
Yeah.
Actually, Glenn, sorry, I'll just quickly jump in on this very quick technical question before I defer to move on to Jasper's question. So just very quickly about the countable additivity thing. I remember you showed on the last slide that there's some convergence result, and I was just curious whether or not you need, for example, in the standard Levy 01 law, you need countable additivity in order to prove it, to my knowledge. So I was just wondering whether or not you need something like that, or do you just don't want convergence law?
That's one of we don't need it. And in my mind, that's one of the great discoveries of our book. You don't need it. That didn't come easily. We worked for many years to get that. You don't need it. You don't need it there. You don't need it for the law of large numbers. You don't need it for anything you want to prove in probability.
So
Now,
do you have a different version of the law of large numbers, or do you just have the same version but you don't need it?
it's a more general version. Law of large numbers. Law of large numbers and Levy's 0-1 law are more general because it's like we don't just do it for probability, we do it for imprecise probability. And imprecise, if we have forecaster in there, then it's really, if forecasters probabilities, if we don't give probabilities for forecasters probabilities, then the law of large numbers in Levy's 0-1 law is a statement about the relation between forecasters probabilities and the outcomes. So measurability is completely out the window, and when we also don't need anything like kind of additivity. Now, since we don't even have additivity, it's a little confusing to say we don't need kind of additivity. But if we go back to Kolmogorov's original book, he didn't assume countable additivity. He assumed a continuity condition, which is equivalent to countable additivity when you have a finite additivity. But we don't need that condition. We don't need that condition.
Oh, but do you assume continuity or version of it?
No,
okay.
we don't. We get the result without that. And if you specialize, so therefore, when you specialize from our general theory to the additive theory, it works even for finitely additive probability measures.
Interesting. Okay, thank you. That's really helpful. Yeah. Okay, Jasper.
Yeah. Okay. So I'm not a philosopher. I'm hearing all these talks, and I just wanted to kind of add my own perspective on this theory and what I think it could do for physics. I have the impression that when you apply it to physics, part of the confusion that arises is the fact that it's a game. I have the impression, and listening to all the questions, it comes down to trying to kind of get rid of the game aspect, and then okay, one of the things was let forecasters is not a player, it's just the theory that you're trying to test or work with or do. So there's the whole game part is out there, and then for the skeptic part, okay, you have the whole let's just making a batch of tests and not just one person trying to strategize, but just like the whole batch of possible tests, and it's never possible to do whatever. But then when people started talking about reality here, it got a bit weird to me as a non-philosopher, and which stuff can you put into reality, and maybe everything is part of reality, and it's just okay. But okay, at some point, Glenn gave a talk in which I think it was very clear that, at least it became clear to me there, that okay, reality is not playing as far as I see it when it comes to testing theories here. It's this, okay, typically if you're testing something, it's about a sequence of things that you're talking. In physics, a series of experiments, or if you want to keep it non-physical, just like coin flips or whatever. And reality is the only thing that's reality is concerned with. It is what the outcome is, like what's the sequence of coins, what's the sequence of outcomes of the experiment. That's it. And there's no strategy in coming up with like how reality is trying to kind of trick you or have a way of doing. The whole point of the theory is that whatever reality does, and that implies it's completely irrelevant. Like if there's a strategy, if there's something inside reality, the only thing that's bad, try all possible outcome sequences, and for all of them, either the theory will hold, so I don't know, the law of large numbers, of which whatever thing that you're trying to kind of test, either you can get infinitely rich. And that is true for all paths. You have paths which you're in all outcomes, there are paths for which you become infinitely rich, and there are those for which the theory is true. And together, they're all possible outcomes. So I had got the impression that some people were kind of confused by what reality might try and be clever and play along with skeptic and whatever. It's totally irrelevant. It's just a statement about, regardless of what happens, either one of these things is true. You get infinitely rich or the theory holds. that's it. So I just wanted to kind of add that to like not make that role of reality so large. To me, it clarifies a lot what it can tell you about the role of some kind of law. And okay, and so then when it gets to what it can do for me, okay, to me the whole point is that it has this very simple mechanism that I just kind of said about connecting statements about simple small things to very complicated statements about large things, like something like the law of large numbers or whatever thing you have is a complicated matter. And it follows by this extremely simple mechanism, as in whatever path you take, you're either infinitely rich or the law is true. And it just follows from some basic starting block. And to me, I'm also confused by the philosopher's distinction between a prediction and an explanation. To me, an explanation is like, in physics, you cannot go out turtles all the way down, right? It's also an explanation is always making something complex sound reasonable, starting from something less complex. And if you understand like how you get from the simple stuff to the complex stuff, making that make sense kind of clarifies stuff in our heads and makes us feel like there's an explanation, but then the initial part you started with, you're still stuck with. You can take this all the way down and never. And so in that sense, I find this game-theoretic thing also very nice. It's just a very clear step of starting from something simple. And maybe you're not happy. I have the impression when they talk about metaphysics, it's more about not being happy with what you started with. As in, I don't know, the description you have for the outcome of one experiment, you know, Born's rule, for example, or these kind of things. And then you start from some statements, some ways you want to bet there. And then you do whole game-theoretic probability and lead you to other conclusions that follow from it. And to me, the beauty is in this connection. And then I find it strange how the criticism is on the initial point, which I would say that other theories of probability have the very same issue, and yet the way they connect the simple part to the bigger things like law of large numbers just overcomplicated in other theories and made more clear cut in this one. Okay, just offering a bit of non-philosopher perspective, ready to be destroyed by the philosophers if need be, but. That's the whole point of philosophy, right? To be destroyed and then destroy back.
I don't disagree with much of what you said, except these jabs against philosophers all the time. First of all, Glenn was the one who introduced the distinction between prediction and explanation. And second of all, I mean, a statement like everything is part of reality? What's such a mind-blowing, confusing statement? Isn't it obvious everything that exists as part of reality?
Agreed. I just didn't see the relevance for game-theoretic probability here. As I just wanted to clarify that what's meant by reality is not this big thing that we can philosophize about, but it's just all possible outcome sequences, and then that's it. And the fact that at least one of two things will be true for all of them. That's just wanted to clarify that when it comes to the meaning of that word here in the theory, as I understand it, it's much simpler than this grand view of everything, so to speak, that we also tend to associate with the word reality. And as for bashing on the philosophers, it's just a good way to initiate an interaction, as this doesn't say anything about my views on philosophers. If anything, then that they are one of the few scientists that can take it and then engage with you if you do so, which most other scientists no longer do. So I thank the philosophers for that.
I don't know. I disagree with that being a good way to initiate.
Can I just say one small thing? Sorry, maybe Glenn, go ahead.
Oh, I had a completely different thing to say. Go ahead, Eddy.
Okay, just kind of say my personal view on explanation and different from between explanation and prediction. So prediction can be very pragmatic, extracting predictions from physical theory about some kind of outcome I'm going to do in the next 5 minutes. And there can be lots of pragmatic ways to extract predictions. Sometimes there's not a canonical way to do it. But explanation, I think, should be regimented in a careful way. And there are lots of different ideas about what a good explanation is. For example, there is the DN explanation. That is, you try to explain things by deducing them from the fundamental laws of nature. And we can add further things. For example, the laws should be simple, should be compelling, should be explanatory in themselves, but they're at the beginning, they're the bottom of explanation. You start from laws and explain patterns from laws. And if the laws turn out to be complicated, then that's probably evidence that we had not searched for the right laws. If the laws turn out to be incomplete, then we have to find more laws or other laws. If laws turn out to be incorrect, then that's evidence we should reject the laws and try to find new laws. But there is this idea that there is some turtle at the bottom level of reality, and that turtle is the fundamental laws of nature. And it's not, there's no further turtles all the way down. So this kind of in agreement with people like Weinberg, dream of fundamental theory. You have the simple, compelling laws being the axiom of fundamental physical theory. And they may include probabilistic laws, or maybe completely deterministic.
Yeah, I would just say, though, that, I mean, you don't have to assume from the outset that probability itself is one of the turtles, right, at the bottom. And I think that's in a way what happens with this game theoretic approach, is that it doesn't assume that. And then you try to sort of recover as much of a underlying picture as you can. And in some cases that might be possible, but in some cases it might not. If you have this kind of starting point.
Right. Yeah, so I'm sympathetic to that, thinking about the possibilities abstractly, thinking that something is either in the world, in the mosaic, the human way, or in the laws, or it is something else. But then we have to have a new category for the probabilities. Then what is the probability category? Is it something like in our minds? But is it purely in our minds, since it's intersubjective? And that becomes a question for how do we explain that all of us should use the same probability distribution, say the Born rule, for making predictions in quantum mechanics. And the quantum Bayesians sometimes go extreme and saying, well, there's not all, just you. You are the person in the world making predictions. And sometimes folks saying things like, almost something like solipsism, that we should think that quantum mechanics is for you, just you, not you and me, just you.
When I was, this is kind of a very unphilosophical comment. When I was in the mid-1960s, when I was an undergraduate, I did take some physics courses. My physics teachers were very prominent people. I think one of them got the Nobel Prize for something. But I don't remember them having these kinds of philosophical views. In fact, I think they said things that seemed very different to me. One of them, I remember so clearly this great lecturer, my first physics teacher in college. One day, he sort of stopped what he was talking about and told us, I want to tell you the difference between a mathematician and a physicist. He says, a mathematician, and he had a whole bunch of diagrams on the board. He says, a mathematician wants to find one place to start and then get everywhere else from there. He says, physicist doesn't care. Physicists can, it's interesting to them to start here and go there, or they might start here and go there, and he drew all these different arrows on the blackboard. That seemed like a different philosophy of physics than I'm hearing here. Do you think the physicists themselves have changed, or is this just the way people in the foundations of philosophy look at it?
So by the way, that describes what Feynman calls the Babylonian conception of physics. There's no privileged starting point or axioms. You can start anywhere and get to the same thing.
He called it what?
The Babylonian conception of physics. Instead of the Greek conception of physics, the axiomatic conception.
I see.
In chapter 2 of Feynman's The Character of Physical Laws,
I see.
Remember what
So he-
happened in the Tower of Babel?
Maybe that's related too. I'm not sure.
So Glenn, of course, physicists have all views all over the place, and there's a gigantic fight. I mean, there's the dissing of philosophy by some physicists is quite well known. On the other hand, so for example, there was a book by, I forget now, this cosmologist at Arizona State. What's that guy's name?
Paul Davis?
Nothing guy, what?
Paul Davis?
No, the guy at Arizona State who wrote why anything exists, or how the universe came out of nothing. But anyway, it was full of dissing philosophy, as Feynman did sometimes. And of course, Feynman himself raised philosophical questions, and he made philosophical claims. Like, nobody could possibly give an account of what's going on in the two-slit experiment. And yet Dustin can give an account because he knows Bohm, I could too for that matter, or Bohm could, or Broglie could, because there is an account. Okay, it might not be one that Feynman would like. Okay, but the idea that physicists diss philosophers, some do, some don't. Einstein didn't. Einstein had a great deal of respect for philosophy, and physicists' philosophical views are all over the map. I mean, philosophy, just like any other subject, has its own traditions and its own knowledge and things that have been brought up in its own subject matters. Okay, and whether physicists need to learn about it or not is not something I want to say. It's that, but there are a lot of problems that philosophers of physics are interested in.
Yeah.
Maybe
So
okay,
thank you for that clarification. It was just sort of in my head, the comment.
Can I think one issue that would be helpful to separate, in particular in regard to the problem of explanation. I mean, for me, being a determinist, I'm mostly thinking about applications of probability in physics as pertaining to effective non-fundamental laws, right? And then the kind of explanation I'm after pertains to theory reduction, so to speak. Like, how do these statistical regularities, the probabilistic laws, right? How are they grounded in or explained by the fundamental laws? When we talk about the fundamental physical laws, then we quickly get into this metaphysical debate between Humeans and non-Humeans, whether it makes sense to ask, to say whether just the world as it is, the actual world as it is the baseline of everything, or it makes sense to ask a further why question. But why? Is there something that makes it necessary for certain things in reality in the world to evolve as they do, or to be as they are? But I think that when it comes to like effective laws, and I mean statistical mechanics usually deals with effective non-fundamental laws, I think then there's a relatively uncontroversial sense in which we want to explain statistical regularities. We want to explain the second law of thermodynamics. We want to explain Boyle's law. We want to explain the Maxwell distribution in the sense of what is it about the more fundamental physical laws that make them true, regardless of how these fundamental laws are conceived metaphysically, right? And I mean, maybe there are two issues to pull apart. And if we talk on the fundamental level, I think it's a completely rational position, the Humean position, to say reality as it is just the baseline. And then the question is just what is the optimal summary of that, or what is a good theory that will pass the skeptic's test? But if we ask about, effective laws, right, effective statistical regularities, then we don't want to take them as the ultimate baseline. We want to reduce them to something more fundamental. And then there is a question about what is doing this reduction, right? And we don't want to take reality in the sense of, the answers that reality gives in in the game as primitives. Sure, does that make sense? At least this distinction.
Yes.
I just want to jump in to say goodbye because I'm just really starting to fade here. I'm about to turn into a pumpkin at midnight. And so thanks everybody very much for the discussion. And
thank you too.
Okay.
Thank you, Leah.
Bye.
Bye.
Hi, thanks.
Hi, Leah.
Actually, I'm going to take off soon as well. And thanks, and also Glenn is the host, so you should feel free to continue the discussion. And yeah, and thanks everyone. Bye.
Thank you, Snow.
Bye.
Thanks, Snow.
So,
Dustin, I presume you were asking to me. Does that make sense? The distinction.
Not exclusively, but not exclusively to you, but.
But yes, I think it makes perfect sense, and in my view, the whole game-theoretic thing has lots to offer when it comes to going from the baseline basically to the regularities that you talk about. For me, going from the baseline to the regularities, there which to me are all kind of come across as variations on basically the strong law of large numbers, but then like other types of this style of things deriving these kind of bigger things from many small things. And okay, to me that's where the power of using game theory as a explanatory thing lies. But for you, it isn't explanatory then making that step with game theory or game-theoretic approach?
Where, again, that might be due to my not understanding the framework well enough, but I'm not sure I understand what does this reduction happen? Like, how does it help to reduce effective statistical laws to more fundamental laws?
what is effective? What are you using the word effective to me? I mean, I don't have an answer to your question, of course. I don't know enough physics, but what do you mean by effective?
By effective, I mean non-fundamental. But maybe, I guess maybe that doesn't help.
Yeah.
Although I'm not sure how to.
Here's a since we're all still talking, here's kind of a odd question. And you know, because Jasper was talking about everything, law of large numbers and variations on it. Of course, there's this law of the iterated logarithm in probability theory that says that it's not just that you converge, but that, you know, to the probability, but that you'll do so in a certain way, at a certain speed. For example, you don't converge from above. If someone did an experiment, particle by particle, looking at the you know, quantum mechanics predictions and found out that the law of the iterated logarithm was violated, would that be considered, you know, evidence? Would that be considered a failing of quantum mechanics? Quantum mechanics. Does quantum mechanics tell us that aspect of probability should be respected or not?
Glenn, may I ask maybe a stupid question about Cournot's principle?
Yes, I'd be glad to respond, but I was wondering what Dustin, if Dustin had an answer to my question.
Okay, so
I don't know. I have to think about it.
Okay.
Not right now.
What did Blaine ask?
yeah. So Glenn, according to, if for example in the lottery, so the winning probability is extraordinarily low, right? But so according to Cournot's principle, does that mean that it can be written off? It can be written off. There's no probability of winning. That does not make quite. That doesn't sound intuitively make a lot of sense. But and also according to your game theoretic probability, you're saying that you cannot win by a large time. So right, but this what accounts for as a large wing by a large time. So that's some
very roughly speaking. The correspondence is multiplying your money by 20 is like a probability of 5%, 1/20.
Yeah. So then,
as far as the lottery paradox, of course, that is what that's always the great debate about Cournot's principle. Anyway, the tedious debate, if you will, about Cournot's principle is lottery paradox. So the point is that if you have a large, if you have 10 to the 24th different possibilities, some of them, you have to have some way of describing them. And some of them will be easy to describe and some not. So it's the easy ones to describe that aren't going to happen. That's the theory. That's, I think that, or something, or else it's something remarkable, something specified in advance. There are many, but there are many applications of probability, not just in physics. So in physics, we have this extreme, as I say, 10 to the 24th possibilities. That's a pretty big lottery. In other applications of probability, it's it's not as comfortable. Yeah.
So a very small probability. So it's only like acceptable when it is like grounded by some like physical law or some pre-set up lottery. So as it has to be, you need to have a more sound grounding for it to be accepted. Is that the Cournot's principle?
Well, I can put in the chat, if you go to our website, I have a paper, working paper number 60 at www.probabilityandfinance, called The Many Faces of Cournot's Principle. And the point was, there's not just one version of it. So that's why I'm being a little flippant. It's like, it's like this principle is always there. And Cournot didn't say that it was easy to apply, but Cournot said it's the only thing that you can, it's the only way you can make sense out of probability as an objective theory. Objective theory, you got to do something like this. And it's not, sometimes it's hard to make sense of it, but it's the only way you can, it's the only thing you can do. That was his view. And then other people have said it all kinds of different ways. And some people don't like it. Some people take your objection to be knockdown argument. That's it. Yeah.
So maybe the more like Kolmogorov, maybe more formalized ability.
Kolmogorov agreed with Cournot's principle.
Oh, okay.
He said so. Yeah. But he's just one person too.
Yes, but maybe taking this, maybe taking the more formalized probability to be to give it a more like a stronger sense, can avoid this vagueness.
He didn't think so. In his famous 1933 book, he had like a 1 page about how to apply probability to experience the world of experience. And that's where you'll find out he expressed Cournot's principle.
Okay. Thank you.
Now that we have some people with some knowledge of physics here, might I drop in a question? When it comes to game-theoretic probability, another feature of it, as Glenn said, is the fact that you don't need to be precise. All the stuff they're doing also works if you're not specifying a full-blown probability. And this could be just, you give, for example, one parameter of it, the mean, or some kind of some features of a probability. But more generally, their theory also applies even to contexts where, for example, that mean may not even be known, may for example, be bounded. And so, or if you put it in terms of prices, your buying and selling price for some gamble may not be the same. There may be some gap in between there if you phrase it in that language. So the whole framework of game-theoretic probability is also applicable to that kind of thing. And I was wondering, like from the physics side and the philosophy of physics, is that a feature that's into play into the discussion? As in, can we making disruption of like, can we describe all there is to physics with probabilities, or do we need more than that? Because okay, it's some standard things like Born's rule and things like that predict probabilities that adhere to probabilistic rules. So you tend to there, I think, try and get to that. But is this there may not be a single probability that describes what's going on. Feature of game theory is that a feature that from a physical point of view is deemed interesting or disregarded as no, that aspect is definitely out of the picture?
No, I think it is interesting, and I mean, if you go to the philosophical debate, I guess that's actually a debate that we are between, for instance, Barry and the typicality people like Eddy and me, that Barry really wants to have a probability distribution on the fundamental level, and we think that well, A, you don't need it, and B, it's questionable if it's even meaningful to basically assign a probability to any conceivable physical event. So that's why I said that I very much sympathize with this aspect of the game theoretic approach, that you can make do with less than a full-blown probability measure.
It doesn't make sense for Dustin and I to replay our debate, but you can find it online someplace. So we had a debate about this.
Any references on this? I might check out that you can put in the chat.
If you send me an email, I can send you the paper I wrote about it.
Okay, fine.
I mean, there's a lot of philosophical presuppositions, and there are a lot of reasons on both sides of this discussion. And I think it's, in my view, it's not a settled matter. And maybe Dustin thinks it is, I'm not sure. But I think there are answers I have to his worries about the meaning of probability. And I do think they raise good questions about the epistemology of the being an exact probability distribution. So it's okay. It gets to be a pretty, an esoteric philosophical debate in some respects.
But I think you wouldn't disagree that one could make do with less than a probability distribution, but you think it's a really good and nice thing to have, right?
It depends what you want to do.
Yeah.
You know, I mean, I usually make do if I don't have any garlic. I use garlic salt.
Since we're still talking, I'll respond. I'll add something to something that Jasper said about reality as a player. There is one theorem in our book, in Wolfgang, my book, where we have a strategy for reality. And this involves a version of the strong law of large numbers where you worry about whether the variances are small enough for the law to hold. So if the variances, let's say Kolmogorov had a particular theorem where he said, if I don't know, the sum of 1 over the variances converges to something less than infinity, then the law will hold. But you can't count on it if the variances aren't that small. Mm-hmm. And of course, how do you prove that part, that you need to have that condition? Well, the way you prove it is if that condition is not satisfied, then reality has a strategy that beats you. So the reality is kind of, so the theorems about what skeptic can accomplish, that skeptic can, make money unless reality and forecaster agree. It's a worst case theorem, and the worst case means no matter what reality does, strategy or no strategy. But there is room in the mathematical theory to sometimes think about strategies for reality. there's also room to think about strategies for forecast. And this is when we talk about defensive forecasting, and it's what Francesco will be talking. I think it's related to what Francesco is going to be talking about in April in our seminar. So can you, if you don't have any theory, if you don't have quantum mechanics, what if you didn't have quantum mechanics and you were just making round by round predictions? Could you hit upon a successful forecasting strategy? And the answer is, if you want to restrict yourself to forecasting strategies that only use certain information, then you can kind of adaptively get there and compete with the best of all theories. That's to me, that's very interesting. And in that case, you don't have to have, for the individual predictions, you don't have to have one-sided or upper provisions. You actually have probabilities for those individual predictions, not globally, but for those individual predictions. That's what we call defensive forecasting. And it gives some insight in my way of thinking. It gives some insight into why statistics and machine learning can be as successful as they are. The probabilities, maybe game theory probability can teach us that probabilities don't actually mean as much as we thought they did.
By the way, even in Bohmian mechanics, I mean, you have a deterministic theory in continuous time, and you have the precise square density that in principle, is equivariant and defined for all times. But then if you want to really prove that typical time-like ensemble, want to prove that typical time-like ensembles are approximately Born distributed, you still look at discrete measurements with random stopping times. So I'm aside from the fact that you mentioned that you can also do the game theoretic approach in continuous time, I think I'm not worried at all about the discrete time aspect. I think that ultimately I agree that the empirical regularities that we want to account for are ultimately discrete observations.
Yeah, I think that's why, in my view, game theory probability can be a very useful tool for clarifying methodological principles we use in physics, statistical physics, for example. And this doesn't, and actually, it's not incompatible to say that we should not use this for the metaphysical foundation if we're realist and want to be a universalist about fundamental physical theories. So we can have the fundamental physical laws given by probabilities that are non-game theoretic, but how we test, how we do predictions might still be using game theory probabilities. So we can distinguish between fundamental metaphysical probabilities from the agent central or agent relevant probabilities for how we test the theories.
So I think, I don't work on philosophy of quantum mechanics. And so debates about whether there really is a precise probability distribution, I'll leave that to Barry and Dustin. But I do think that, for me, there's something more than just the surface frequencies. There's some underlying facts about the process that explain why they are what they are. But that doesn't mean that it's actually precisely correct to say that this underlying mechanism let's say in an evolutionary, I think about evolving biological populations as kind of complicated machines. And there are probabilities that are characteristic of them at least you can model them as probabilities. Like probabilities are a good way to model what's going on. That doesn't mean that in the same sense that some people would think quantum mechanics have underlying probabilities, that doesn't mean that there are precise probabilities that really precisely characterize what's going on in an evolving population of organisms. It just means it's a good way to model them as if they, you can use measure-theoretic probability. It works pretty well. But from that point of view, game-theoretic probability could work also just as well. And because the underlying reality from my point of view, an evolving population does not involve anything that is precisely characterizable by measure-theoretic probability. So to me, that's maybe a difference between quantum mechanics and everything else, including statistical mechanics. That maybe I'm wrong about statistical mechanics, but I think once you get beyond statistical mechanics to social sciences and biology, things are just very complicated and messy. And
I think
the most you can do is model it. Yeah, sorry.
I think your point about a theory of how things came to look probabilistic, if that's what I took from your saying.
Sure.
I think a prime example where that makes sense is financial stock market. Why? I mean, in the stock market, our game-theoretic approach, the idea that you won't make money, is called the efficient market hypothesis. Why are markets efficient to the extent they are? There is an explanation. It's because somebody else has already tried everything. And they've milked out those opportunities. So there is a theory. It's a kind of vague theory, but some people, I suppose there have been some efforts to model it with simulations. It's not the kind of thing you can publish. So I can't cite, you can't publish simulations in finance theory. So I can't cite, where they said it in the literature, but everybody understands things that way. That there is an explanation for why the finance market looks probabilistic.
But, and does it, the people who give that explanation, do they assume that there's a precise probability distribution that over what the market will do?
Well, it's like Barry was saying about philosophers, there's all kinds of views, yeah. But too often they do have a kind of over precise concept of what's going on, in my opinion.
Mm-hmm.
What was your explanation? So the market is efficient because people have, I don't know. What
is efficiency? I mean, I think in games, from the game theory point of view, it's easier to explain, easier to state the idea. What is in the market, today's price is a prediction of tomorrow's price that you can bet on by buying the stock or selling it, right? And the efficient market hypothesis says that today's prices are a good prediction of tomorrow's prices, that you, Dustin, are not going to make any money. Which stocks to buy and sell. More precisely, you cannot multiply, you can't create a non-negative martingale that gets big. You can't multiply the money you risk by a large factor. That's the statement that those predictions are good prices. They're like Dustin was talking about. They're not complete probability distributions, although you can complete the market with options, etc. But forget that. You're just looking at the prices. So it's like expected values without probability distributions, but still they're prices you can trade in. And why are those prices so good? Why is it that Glenn and Dustin can't make money trading in those prices? Is because all the strategies that are simple enough for us to try and compute are constantly being tried by somebody with more money than us. And the market has, adjusted to the demand and wiped out any ability for anybody else to use those strategies. And I think there's probably, intuitively, there's something in Marshall's domain of evolutionary biology. You can think that there's that probabilities could be emergent from, and people have written about that, I think. Probabilities are emergent from the competition. Cournot also wrote, Cournot wrote economics books. He's best known as a theorist of economics before his time. At the time, the economists didn't pay attention to him, but he's now known for his theory of oligopoly. And he doesn't really explicitly talk very much about probability in his economic theory. But he does have this idea that the laws of economics aren't really working very well until there has to be some evolution. You have to get an economic system and a governmental system where you have effective competition before you can get so he kind of had an emergent concept of regularity in economics too.
So does
sorry, I need to go here. I have about 6 hours left until my children wake me up. So I have to go. Thanks a lot for a very nice discussion, and maybe see you some other time. Yeah. Ciao, guys.
Oh, Dustin, it's practically morning for you.
Yeah,
it's like 1:30 a.m. But I'm used to going to bed late, so meeting early in the morning would be worse for me than
I have to go soon too. By the way, just one last comment maybe about precision and exactness of distributions. So there are lots of interesting discussions about imprecise probabilities, the kind of coarse grain probabilities in stats and probability theory. So I was thinking that, and we have this discussion before, Glenn, that really to have imprecise probability, we can't really describe the imprecision using set theory. Even a set of probability distributions, or upper low probabilities, or some kind of range of numbers, range of probabilities is still too precise. Doesn't really account the phenomenon of high order vagueness, kind of vague probability distributions. To have a really vague probability distribution, we have to allow high order vagueness that cannot be modeled by set theory. It's one of the upshots of discussions of vagueness in philosophy of language and logic, which is very hard, maybe orthogonal to this discussion. But I wrote a paper called, sorry?
Well, no, Jasper is now gone from the discussion, but I mean, I agree with you, but I think it's that community Peter Wally chose the wrong name.
Right. I think we talked about this last time too, but there is some sense in which typicality itself and game-theoretic probability and Cournot's principle are inherently vague. There is this kind of threshold question: what is large enough? What is typical enough? And there's the property question: what property do we use to fix the typicality class? Which worlds are typical relative to some kind of property? So all of these are sources of vagueness, but not just sources of imprecision, but kind of really high order vagueness. And it shows something that if typicality or Cournot's principle or getting probability are central to how we reason, and reason itself is vague, there is this kind of high order vagueness built into how we reason about probability, which I think is not always kept in the foreground of the discussion, but I think is something that is really shocking to me when I first realized it, because that means the talk of probability is not fully or completely mathematically expressible. Because if mathematics is built on set theory foundation, then all this talk cannot fully or faithfully capture the notion of what we mean by probability or typicality or most. Sorry, end of long rant.
So that seems like a point in favor of game-theoretic probability.
I think it's already kind of a feature of ordinary laws of physics. Say the past hypothesis that Bear Lower and David Alp have argued for many years, that it itself, as a fundamental constraint law of the universe, is vague. And it kind of is it's kind of compatible with the more vagueness physical laws. But already, without thinking about probabilistic laws, even constraint laws, there is a source of vagueness here. But when you think about typicality, in general, there's more vagueness, kind of pervasive in scientific reasoning.
Well, Dustin and Eddy, thank you so much for your generous discussion of these efforts to apply game theory probability.
Thank you, Glenn, for inviting us.
I'm going to go too.
Yeah, I think we're way past Snow had cutting it off of the other panels at 5:30, but this time she let us go on. So this is even recorded for posterity. We didn't stop.
Right.